Welcome to Unit 6 Kinetics. For beginners, this is the study of chemical reactions and how quickly or slowly they go. And so we'll always use the standard. A is usually referring to the reactant, and B is referring to the product here. As far as the reaction rate is concerned, we can measure a loss of reactant concentration and molarity over time, which is also equal to the positive gain or formation of product measured in molarity over time. So whenever you see these brackets, that represents a concentration in molarity. Note this table. MCS represents molecules. So over time, as this reactant breaks down, you'll have fewer and fewer of them. However, you will start forming more and more product molecules. So you can see this over here is A, and this is the curve for B, or formation of products. As time progresses, we can see that the rate will go down, because if you have less and less particles to break down, it will take longer for them to react. And secondly, for the next question, how are we going to measure these changes in concentration? Typically, we can see these reactions in the lab. They usually are identified by a change in color, or a change in amount of gas formed, or some other type of change that occurs that identifies that a reaction is going on. Moving on to part 2, differential rate loss. A rate loss shows how the molarity of the reactants will affect the reaction. So typically, if you increase the concentration, you have more particles moving about, so the reaction rate increases. How do we look at these rate laws? For one, if this were a stoichiometric equation, where A and B now are the reactants, then the rate equation or rate law would look something like this. The rate is equal to a rate constant times the molarity of reactant A to an order of X times the molarity of B to the order of Y. K, X, and Y are determined experimentally, and we could also say that this particular reaction has an overall reaction order of the sum of whatever X and Y are. It's important to note that the rate is equal to the initial rate at the time when this reaction starts. Alright, on to rate law problems. So our ultimate goal in these type of problems is to solve for the rate law, and it will look something like this. Where X and Y are called orders, and they tell us about the behavior of these concentrations in relation to the rates. So in order to do this, we can look at proportions between two trials to figure out the orders. So to figure out the order for A, what we'd have to do is look at trials 2 and 1. You don't have to pick trials 2 and 1, but I'm going to use those to show you what you can do. So you can take the rate of trial 2 divide it by the rate of trial 1, and set it proportional to the trial 2 data, so k times 0.2 to the x times 0.1 to the y, all over trial 1 data, so k times 0.1 to the x and 0.2, that's an x, 0.1 to the y. As you can see here, the 0.1y cancels, and so on the right hand side you're left with 4 equals, no, the constants cancel, you're left with 4 equals 2 to the x. Since 2 squared equals 4, x must therefore equal 2. We can then do the same for solving for y. And in order to solve for y, let's come on over here and use one where y varies, but or concentration B varies, however A stays the same. So for this one I'll use 5 over 4. For the rates, you have 3.3 over 1.65. Point 1 to the x times 0.6 to the y over trial 4, which would be 0.1 to the x times 0.3 to the y. In this particular case, the left-hand side simplifies to 2, and the A concentration cancels, leaving B as 2 to the y. And since 2 to the first power is equal to 2, then y here is equal to 1. To finish this problem off, you still need to solve for k. So we'll rearrange this equation to solve for k. Dividing both sides by the concentrations, we get k equals rate divided by a to the x, which is now squared, 2, and y, which is now 1. We can use trial 1 to solve for this, so we have, using trial 1, 5.5 times 10 to the negative 6 divided by 0.1 squared, cubed, which gives us 0.0055 meters to the negative 2 and over second. Okay. And our final rate law then becomes rate equals 0.0055 times a to the second power y to the first. So the reaction is third order overall, because you would add the second order and the first order together. And this is actually a B. This is a B. Okay, so it's third order overall, second order in A, and first order in B. Alright, and we can continue on to the next problem. A similar problem here, we would do the same basic concept. So if you're going to determine the rate law for this one, imagine doing the same thing. If you look at trials 1 and 2, if you're solving for D, the order of D, you can take the rate of trial I like to make a note where I'm going to put 2 over 1, meaning I'm going to set the proportion of 2 over 1. So the rate data, 1.812 times 10 to the negative 3 over 4.530 times 10 to the negative 4. Set that equal to the k times 0.2 to the x and 0.1 to the y over k times 0.1 to the x and 0.1 to the y. This allows us to get 4 on the left. The constants cancel and the B concentration cancels, leaving us with 2 to the x. Therefore, x is equal to 2. Solving for this time, I'm going to use 6 and 4, trials 6 and 4, to compare, to solve for the order of C. I'll do that over on this side. So 6 over 4. Alright, notice that the rates, the initial rates, are exactly the same. Then setting them equal to the constant, times the rest of the equation for both trials 6 and 4, and now 4. And you can see here this side cancels to 1. Constants cancel, the D concentrations cancel. I'm left with 2 to the y. And 2 to the 0 power will equal 1, therefore y is equal to 0. Now we have to solve for the constant. So step 3, the constant is equal to the rate. I'll go ahead and use trial 1. The constant is equal to the rate divided by the data here in this case is 0.1. Again, D is second order, so 0.1 squared, and then C is 0 order, so that ends up being 1. Anything to the 0 power equals 1. So it's basically, so this simplifies to 1. And you should get a constant of 0.0453. And that would be in terms of, since we have an order here, of meters. Be meters to the inverse meters and inverse seconds. Okay, and we can see that this is overall, the rate is equal to 0.0453. Okay, times, okay, D to the second order, and this would be C to the 0 order, which we usually reduce that and write it as, we actually, since this is equal to 1, a lot of times you won't even see that. And this is second order overall, 2 for D and 0 for C. And that's all, you're done. We'll see you later.